my presentation is on review of rocket noise and review of the progress and understanding of rocket noise is the main objective of this paper, with a focus on noise characteristics, effective forward speed, and noise suppression. Let me give the background so everybody knows about rocket noise. The main sources, noise sources, are turbulence and its interactions with mean flow, shock structure, and the interaction with the solid body. The ignition transients generated high intensity noise sources, and large and small eddies present in the jets are also potential noise sources. The consequence is noise and vibration environment over flight vehicles and equipment, and of course community noise also is a part of it. And main database as of now for the rocket noise is from static firing, subscale testing, and launch measurements, ground as well as flight and onboard measurements. Providing soft payload environment is the main motivation for studies related to rocket noise. And I will go into the rocket noise characteristics, what's known about rocket noise characteristics first, and go on to discuss about the effect of forward flight and the noise suppression aspects at the end. The noise sources of all frequencies are known to be distributed along the rocket exhaust and is described by jet core length, in terms of jet core length, and it's a function of exit Mach number of the jet. And the present understanding is that the peak sound powered region is located 1.5 times the core length, and the extent of powered region, sound powered region, is around 5 times core length, and it is equivalent to, in terms of nozzle exit diameter, it varies from 20 to 35 times the nozzle exit diameter. And the peak radiation can be visualized from the sound pressure contours measured and reported by Mayers on a small rocket engine. As you see here, this is a peak radiation direction, and the noise is located around 20 dB. Sound powered WA can be represented in terms of acoustic frequency eta, so acoustic efficiency, and the sound, the mechanical power of the rocket exhaust, which is thrust into velocity fraction by 2. What is known is a small percentage of this energy is converted into sound power, and this is derived from light field theory, and it is from Professor Ffowcs William, this number, and it is 6 into 10 to the power minus 3 compared to the rocket motor firing, what is obtained from rocket motor firing of 0.5. They compare very well. And if you look at the sound power, for the rocket it is proportional to e to the power 3, unlike the subsonic jets, which is given by light field theory, the 8th power. So this is the reason why the acoustic efficiency is constant for a rocket. That can be seen here. Acoustic efficiency of rocket lies somewhere here. Sound power spectrum is generally used to get the acoustic load on the vehicle. And the Sutherland model is what is shown here. It appears to give reasonably good results for small and large rockets as well as supersonic jets. And the Stockwell number normalizing parameter what is used is A star, that is the speed of sound at the throat. Coming to directional characteristics, the peak radiation, what is measured from the static test, is around 50 to 60 degree for rockets. But whereas in the vertical firing, the measurement shows that is 70 to 80 degree. But the Mach wave radiation angle can be given in terms of convective Mach number if you work out, and it will work out to be 50 to 60. So this experimental value can be reasonably justified, but 70 to 80 degree obtained from vertical firing, it is attributed to the noise, the interference due to ground, as well as the deflector. So, but it's not fully understood whether that explains to and interpret the levels what has been obtained in the vertical firing or the horizontal firing. So directivity index variation with the Stockwell number is another information, that database which is constantly used for getting the noise field. And as you see from here, low frequency waves dominates the downstream direction. The waves in the downstream direction is dominated by low frequency contents, and the upstream is dominated by high frequency waves. In addition to this all behavior, the ignition transient environment is generated. This is an environment phase experienced by rockets at liftoff. It is generated by a large amount of gas injected into the exhaust ducts with interaction due to duct as well as the exhaust, and what is known as ignition overpressure and duct overpressure. These are all the waves generated at the duct inlet and the exit, and they are basically give rise to low frequency excitation on the vehicle. And in addition to this, jet impingement noise is also present at the time of liftoff and creating a critical environment for the rocket, launch vehicle kind of vehicle. This is, as you see here, is the lift off overall sound pressure level variation. This is at the ignition, due to ignition transient, a peak of 4 to 5 dB overall, and at the due to impingement is again more than 5 dB increase. This is actually dominated by the low frequency content. This is the measurement found by measurement of time for the Aryan vehicle, and 31 Hertz band, the distribution shows that the ignition and the impingement peaks. This is the measurement of the payload fairing. Prediction generally is of empirical in nature. Similarity methods are used, semi-empirical methods based on the NASA database. This is widely used, and recent application by Vernier to Aryan vehicle shows that you can do a good job. But what they did, they carried out some modification, that is they express the flow parameters in terms of the fully expanded jet conditions, and they modified the core length of the jet. And recently there are efforts to apply computational aeroacoustics. Basically, they have used what is used for the tabletop rockets. What has been used is the hybrid method due to CFD and Kirchhoff formulation, a combination of this, but giving rise to not very satisfactory results are obtained, reported. Coming to forward flight effect, there again the database like static conditions. Static conditions we have a lot of database, whereas the forward flight situation, generating database is difficult and the database is scarce. And but the factor controlling the noise intensity has been given by Powell, and is a function of jet Mach number and forward speed of the vehicle. As you can see here, noise intensity decreases with the forward speed. But early studies have shown that there are noise increase in the forward direction due to amplification of noise, of shock associated noise. But the recent studies carried out on the supersonic air jets have shown that it is minimal, as suggested by Professor Kruthapalli, that the amplification of overall sound pressure level is around 2 dB, or there is no amplification at all. But what is important is reduction in radiated noise from fine scale turbulence. Sam's theory says that dominant noise sources moves downstream due to the forward flight, and turbulence intensity and eddy size reduces. This is the spectrum obtained from the ground measurements launched during the vehicle lifting off. So these are all from different what we call measurements locations, far off distances, the solid line, and there is a lot of discrepancies from the sound sources, the sound spectrum obtained from different measurements, different locations. It could be due to the fact that they have used a constant directivity factor, and also atmospheric attenuation is not considered. So that this variation can be explained. But what is not seen is the forward speed effect, because this stars correspond to the value, the empirical model on the static condition. So this is not clearly visible. The difference between the forward, the effect of forward speed is not seen here. So noise suppression, so as you know that at liftoff, the vehicle experiences very severe noise levels, and to safeguard the vehicle and the system, the noise has to be brought down, and water injection has been successful, and it has been tried successfully by different people. And for example, 6 to 8 dB noise suppression needed for space shuttle seems to have been obtained by a water spray of 2.5 times the mass flow rate of solid rocket booster and 6.8 times the mass flow rate of the main engine. For Ariane, it has been achieved, seems to have been achieved, the combination of water injection and exhaust duct extension. As you see here, the lift-off noise is dominated by the low frequency noise content, and with water injection they could bring down to this level, but not to that requirement of their expectation, their design level. So that was the reason why they seem to have gone for the extension of the exhaust duct. And so the noise suppression mechanism, though noise has been successfully suppressed, brought down to the desired level for different vehicles, the noise suppression mechanism is not fully understood, and generally reduction is done, the suppression is done with a large amount of water injection, and this is a research by this group, and that is the Onara group. They have seen that the decrease in the velocity due to the momentum transfer and the temperature drop is mainly responsible for the noise reduction. But they have also seen an increase in the noise due to the impact, water injection impact. But there are this investigations on supersonic jets, though it is not directly applicable, but it can be related to the direction. We can infer direction to proceed. You can get direction to proceed for the noise suppression. For example, this is a work of Professor Protopalli and his team. Small amount of water or air injection is able to substantially reduce the noise level. Though it is applicable for aircraft, this will give definitely a direction for the noise suppression in rocket exhaust. Similarly, coaxial airflow introduction by Popomocio and his team eliminates the macro radiation. It's very attractive because macro radiation is the main contributor for the rocket noise. Conclude, seen overview of the rocket noise, physics of rocket noise generation, and the mechanism of noise reduction due to water is not fully understood. Application of new experimental technique based on microphone array. This has been used by Ariane people to a limited extent. And computational aeroacoustics or immediate challenges in rocket noise research, that is to understand the rocket noise, understand more about rocket noise. With this, I conclude.
Now, you have made some measurements on SLV3, right? GSL.
Yeah.
In flight.
Yeah.
You have not showed that. Is it
Uh,
classified or?
No, I have shown what I have shown as the two peaks occurring for a launch vehicle is basically from one of those measurements we have done.
But I remember you also seen the transition, the boundary layer noise too, is that right? And the vehicle is moving up and close to supersonic. The sensors have picked up the noise, right?
Yeah, but configuration noise is not discussed. So I concentrated on the rocket exhaust induced noise.
Mention one of your figures that the peak radiation angle in the experimental data, whatever this is 50 to 60 degrees, while in the vertical firings it's 70 to 80 degrees. What is the reason for that? Were the conditions identical jet temperatures and acoustical Mach numbers? And nevertheless, peak radiation angle was different.
See, it is not fully explained, but I would think that the vertical firing is for a typical launch situation with the deflector and what you call exhaust ducts and things like that.
Mm-hmm.
Okay, they could have contributed, and they could have altered the scenario for the noise generation.
Oh, the ground reflection is included.
Yeah.
Does it make sense to relate the 31.5 Hz peak that you showed to any combustion chamber oscillation, natural acoustic modes, standing wave modes inside the combustion chamber? Because that's too tempting to do. That's around the same frequency for, let's say, large solid rocket motors.
See, this is believed to be due to ignition transients. That is what I have shown it as what is called ignition over pressure and duct over pressure. They are mainly, maybe the combustion would have contributed, but the main contribution comes from the interaction, the jet interaction, the jet flow field.
Would you have a similar water injection scheme for the noise from the exhaust as well as the other big spike you showed for the ignition or pressure, or a similar scheme would take care of suppressing both the noise?
Yeah, that's the literature shows that ignition over pressure also can be controlled by the water injection, but with the selective locations. That's important because nozzle, the duct, inlet, exit, those are all the places where the sources are seen. The injection is advised, or what is seen is the people are successful by injecting water at these locations.
So you need one scheme for taking care of that spike and another scheme for the overall exhaust noise. Is that what it is?
A combination of that can be tried at the liftoff.
Thank you.
Okay, thanks. I think we're probably